All right. Good morning and happy Friday to you guys. So, today we are going to start our next section, which is going to be all about exponentials and logarithms. Unfortunately, I have to be gone today because we are in Wichita right now at the state wrestling tournament. So, please be kind to the sub. Please make sure you get your notes done, and hopefully, you won't have to take any homework with you over the weekend. Okay, so in 9.1, this is going to be our intro to exponential functions. So this is where we're going to talk about what is an exponential function, how can you tell what is an exponential function from what's not, how can you tell when something is growing versus decaying, and then what are those different pieces of the function that we can use to help us. So let's just start with a little bit of review. Let's talk about linear, quadratic, and exponentials. Now, for a linear function, your parent function is this. F of x is equal to ax plus b. That's kind of your general form for an exponential function, or for a linear function, excuse me. Now, when you look at linear functions, especially in a table or a set of points, what you look for is a constant, what's called common difference. In other words, are you adding or subtracting by the same thing every single time? Okay, now for a quadratic function, its standard form, and we've seen different forms for a quadratic. Keep in mind standard form is this, ax squared plus bx plus c. Now, as far as its constant change, it has what's called a constant second common difference. Meaning when you first look for a pattern, you will not see one. It will be numbers that are going up by 9, and then 17, and then 25. But when you look at those numbers, that's where you see a common difference. Okay, now the very last one, the one that we're going to focus on today, is going to be exponential. And we've already seen a general form for exponential. We saw that in the lab from last Friday, and I know it's been a week. So here that is, f of x is equal to a multiplied by b to the power of x. Now, we look for something different. We don't have what's called a common difference. We have what's called a common ratio, meaning that you are either multiplying or dividing by the same number each time. Okay, so now let's determine whether each of these functions is linear, quadratic, or exponential. Now, what you need to look for when you're looking to decide what type of function it is based on an equation, you look for the degree. The degree tells you everything you need to know about that function. For a linear function, it will have a degree of 1. For quadratic, a degree of 2. And for exponential, it has to have some kind of a variable as the exponent. Okay, so on number 1 here, as you notice, degree for our equation is a 1. So this would be an example of, and it doesn't look like it normally would, but a linear function. Now for the second one here, you notice that the variable is an exponent. That's going to be what makes this one exponential. Now for the third one here, you look for your degree. Here it's a 2, so that this last one would be quadratic. All right. Now, when you're looking at it based on a table, you have to do so just a little bit differently. So look for the pattern. On this first one, 6 to get to 10, it looks like you'd add by 4. 10 to 14, add by 4. 14 to 18, add by 4. This is what an example of a common difference would be, meaning that this one is adding or subtracting by the same number each time, so it's going to be linear. Now the second one here, if you try to add, notice that you're adding by 2, and then 6, and then 18. Not a pattern. So next thing you want to do is look for multiplying. Let's see, 1, you'd multiply by 3 to get to 3, 3 multiplied by 3 gets you 9, and then 9 multiplied by 3 gets you 27. So this would be an example of an exponential function, because you are either multiplying or dividing by the same number. Now, this last one here, to get from negative 2 to 7, always check for addition first. You'd add by 9. 7 to get to 34, you'd add by 27. So right away, it's not going to have a constant common difference. And for multiplying, to get from negative 2 to 7, you'd have to multiply by negative 7 over 2. 7 to get to 34, you'd have to multiply by 34 over 7. So you're not multiplying by the same number each time. So that's going to be where you look to see if it's going to be quadratic, meaning find the first common difference. So here you would add 9. Here you would add 17, or 27, excuse me. 7 to get to 34, add by 27. And then 34 to get to 79, you're adding by 45. Now, what you do to see if it's quadratic is now you take each of these numbers, 9, 27, and 45, and you look for a pattern between those. So from 9 to 27, you add by 18. to get from 27 to 45, you also add by 18. So if you notice the second common difference, not the first one, which would be this first kind of set of numbers, but your second common difference is a pattern, meaning that now you've got what's a quadratic function. Okay, so now let's talk about the pieces of an exponential function and kind of what it looks like. So we already mentioned exponential functions look like this. F of x is equal to a multiplied by b to the power of x. Now each of those pieces means something. A is your initial value. It's your starting value. It's what you begin with. It's also later on going to be what ends up being your y-intercept. So as you think about your initial value, be thinking y-intercept. Now, this piece B, this is what's known as your base, or sometimes known as your multiplier. Now, lastly, you've got your variable here. Your variable, notice, is an exponent. This is going to oftentimes, as the variable, represent time. Not always, but often. And those are your pieces of an exponential function. So when you go to write exponential functions, here's what that needs to look like. Especially if they give you a and b, that should go very fast. To where on number one, all you'd say f of x is equal to, write a first, multiplied by b, which oftentimes I will put b in parentheses. You don't necessarily need to, but it's a good habit to. And then put your power of x. Now, number two, I want you to try on your own. Keep in mind it might not just say a equals b equals. It might say start value, where you'd have to recognize that means a. Or base, recognize that means b. And then write your exponential function from there. Alright, now let's talk about exponential growth and decay. The biggest thing, and we mentioned this a little bit in that activity we did with the M&Ms, but the biggest thing to look at is the b value. If b is bigger than 1, that's what tells you growth. If your b value, what's being raised to the exponent, is smaller than 1, that's what represents decay. Also notice on the graphs that as your x values increase, your y values increase, that's how you would know growth. For decay, as your x values increase, your y values decrease, that would be another thing that told you decay. So then really all you got to do, if you want to note based on an equation whether something represents growth or decay, all you have to look for there is whatever's being raised to the power of x. So here 2.5 is bigger than 1. That would tell you growth. Okay, so 2 and 3, try on your own. And then what I want you to do is come up with an example of a function that would be hard to decide whether it's growth or decay. So think about what you're looking for when something is growth or decay, and think about a number that maybe as a base or a multiplier would make it a very tricky problem. Alright, so that one's going to be on your own. Now, we're going to go through one more example here, and if you notice, I'm going kind of fast today. Notes are on Schoology, so you can feel free to go back and copy any of those down that you missed in the video, or go back and replay the video if you need to watch it one more time. Now, as far as finding the multiplier, because sometimes you're not going to be just given here is b, or here is your multiplier. You're going to have two different things that you're going to have to do. Make sure you first change your rate, change r to a decimal. And then in step 2, you either add or subtract from 1. Now, keep in mind if it was the number 1, nothing changes. That's just constant. So by adding to 1, that ensures that you're bigger than 1 is growth. If you're decay, you're subtracting from 1, so that would be your decay. So for growth, once again, you take 1 plus your rate. For decay, you just take 1 minus your rate. Okay, so I'm going to do one with you, give you a chance to try a couple on your own. So first thing you need to do, look at example 1 here, is change whatever your percent is, your rate, to a decimal. So 3% as a decimal, divide by 100.03. For growth, that's going to be your clue to do 1 plus. So what you would say for your base, your multiplier, take 1 plus 0.03, which is 1.03. There is your multiplier. Now, notice it also wanted you to write an exponential function, and it says that we're going to assume that our a value is 2 for each of these. So when you write your function, you would just say f of x is equal to a, which is 2, multiplied by b, we just found was 1.03, to the power of x. Alright guys, that's all I've got for you today. 2 and 3 you can try on your own. If you're looking to check your work for any of these examples, I do have the notes key posted on Schoology for you. Also just keep in mind that you can always watch the video one more time. Homework is posted as well. Homework answer key is posted. So hopefully you get through the notes and homework in plenty of time in class today and don't have to take anything with you. On Monday, we will continue this unit. We are going to be talking on Monday about logarithmic functions and kind of how those work and an introduction to those. Make sure you do have a calculator with you that day. So make sure if you do have a graphing calculator that you bring that. We are going to be using those most of Monday. All right, guys, have a great weekend. I'll see you on Monday.